Now let's try to see another example where, apart from writing the mathematical equations of our model, we are actually solving those equations. In the case that we have seen before about the RLC circuit, we simply limited ourselves to writing the equations. So we are considering a simpler model. If you remember, we have already seen it in the previous class. This is the Malthusian model. It tries to model the dynamics of a population under assumption that we have infinite resources. So if you remember, the model was written in this way: x dot was equal to ax with a parameter that was greater than 0. If you want to see this as in terms of a block formulation, we have to choose again our input and our output, because in control theory we have inputs and outputs. Without inputs we have nothing that we can control. Without outputs we are not seeing anything from our model. So it's a bit like having no goals, because we don't know what kind of behavior we'd like to modify. Well, the case of the Malthusian model at least is a little special in the sense that, sure, it makes sense to observe the population, so y is equal to x, but the population is not controlled, at least in this model, and so we have no input. So as a definition, I can give you this definition: system with no input is called isolated system. And in control theory, isolated systems have very limited interest because they cannot be controlled. We can only watch them do what they are going to do. That doesn't mean that they are not interesting, and also they are not useful to understand other things. So far we are considering this Malthusian model, and then later on in this course we are going to add an input to it. So far, the only thing that we'd like to do is, if we call the state x, as you can see, we have a state representation that is x dot equal to ax. If you want to write the input output implicit representation that we have seen just a few moments ago, well, that's as easy, because you replace x with y, you subtract yx, the ax, that is actually ay, equal to 0. So in this case, as you can see, this has the form x dot equal to f of t x u, where there is no u and there is no t, so it's a simpler function. And in this other case, you have a g of derivative with respect to time of y that we have learned that we can write this as y dot we start with y dot and we stop there, and then we'd like to have u, potentially u dot, and so on. All these terms here are not there, and also we could have time, and this has to be equal to 0. So in this case, this part is not there, this part is not there, so we have this input-output implicit representation expressed in this way. We are actually lucky because we can actually make this representation explicit when you can take the highest order derivative of y and make it equal to the rest. We can call it this explicit input-output representation. And so, to make it explicit, we simply find the derivative of the highest order of y, and we try to solve the equation with respect to it. In this case, we get something that is analogous to the state representation. Oops, ay. So in other words, we make the highest order derivative of y, the output, as a function of all the other variables. It's not always possible, but when it's possible, actually we prefer to do it. So when we have our input-output implicit representation, typically comes out from some physical considerations that we can make to obtain a differential equation, because that's it's nothing else than a differential equation. The problem is that the highest order derivative of y might be in some complicated relationship with all the rest, so we might consider enough to have this implicit representation. But if it's possible actually to solve for the highest order derivative, we write an equation that is a little nicer, because now we have the highest derivative, the highest order derivative of y as a function of all the rest. Okay, let's proceed. Let's proceed with solving this this equation. We can solve. They are absolutely equivalent differential equations, both in the state representation or in the input-output representation. We are dealing exactly with the same quantity, and I assume that everybody knows how to solve them. So solving the equation is quite, I'd say, immediate. I choose to go with the state representation. It means I'm using the variable x instead of calling it y. So if this is the equation, we know that we can separate the variables, so we can have something of this form, equal to a dt. Now that the variables, all the variables in x, all the quantities depending on x are on the left hand side, all the quantities depending on time are on the right hand side, we can integrate. So we find that the logarithm of x is equal to at. But an important thing when we are integrating is that we are integrating, this is what's typically done, but I prefer to do it in a more principled way. And the principled way, so to speak, is the following. We integrate from 0 till time t. So when we integrate from 0 till time t, the integral of this is given by the logarithm of x at time t minus the logarithm of x at time 0. This is an initial condition that needs to be known so that we can solve the equation. If we are just given how the population dynamics works here, we are not able to solve the equation. We miss some information. We need to know the starting point. Given different starting points, we are going to have different dynamics for the population. So that's why I prefer to be specific when I say that I'm integrating from 0 till t. The integral of these quantities here. Oh, of course, I should have the absolute value here, but I am under the assumption that x of t, x is always positive, because it represents a population. So this is the left-hand side, and when t is integrated from a is integrated between t and 0, we simply have a of t. So if we write this better, we can write this as the logarithm of x of t divided by x of 0 equal to at. There is also the assumption that the population at the beginning is non-zero. X, we assume it's always positive. If the population is 0, we already know what the solution is. The population is going to be 0 at all times. So Under this assumption, we can safely divide by x, or we can take the logarithm of x of 0. We take the exponential on both end sides, so we find that x of t divided by x of 0 is equal to the exponential of at, and this implies finally that x of t is equal to x0 exponential of at. And this gives us the solution of the Malthusian equations. If we want, we can decide to plot it on a graph representing t on the on the horizontal axis and x on the vertical one. Given the initial population, we see that it grows exponentially.